Alright, day 3 is mass, and we looked at the various ways of measuring mass. The formal definition of mass is a measure of an object's inertia, where inertia is an object's resistance to a change in motion. The more mass you have, the more inertia you're going to have. The harder it is, to change your motion, whether you're already moving or if you're standing still. An easier definition is basically how much stuff is in an object. Now, there is something to note that there is a difference between mass and weight. Your weight of an object is basically the force of the gravity acting on you times your mass. So mass times gravity is the weight. Most scales are going to weigh you. We weigh ourselves in pounds in the English system, and the metric systems, it's in newtons. But your weight's not the same depending on where you are in the galaxy, the solar system, even on the planet. For example, let's say I have a mass of 100 kilograms. I don't. I wish I did. That means I weigh 980 980 newtons. If I were to go to, say, the moon, it'll be a sixth of that. And the space station, I probably won't be able to weigh myself because I can't step on a scale because there's not enough gravity. So your weight is not conserved, but your mass is always going to be the same because I'm still going to be 100 kilograms at that space station. It's not magically going to go away. I just won't be able to step on a scale. So that's what the second line means right here, where it says weight is not conserved for an object, but its mass is. So your mass always is going to stay the same. Can't write. Let's try this one more time. There we go. And I mentioned the force of gravity differs depending on the location on the surface of the Earth, and I'll show you that here in a second. But a triple beam balance, a blue balance, and an inertial balance all will measure mass. Mainly because you're comparing one mass to another mass. Even the triple beam balance, basically when you move those blocks around on a triple beam balance, you're still finding the mass because you're comparing two known masses. A spring scale is calibrated, and then because it's calibrated, it's actually measuring weight because you're not comparing its weight, the mass of an object, to the mass of another object. You're comparing the mass of an object to the stretchiness of a spring. So this is really sad, but I actually started this video and I had to quit. But this little inertial balance video it's going to show you, it's completely gone. The YouTube account is not associated anymore, and I don't even know where I got it from. It's a little bizarre. I don't know what's controversial about a video that shows a guy finding his mass with an inertial balance in space. It's really cool, but sorry, I can't show it to you, and I can't even find anything similar out there. It was bizarre. I thought it was on a NASA website of all places, but yeah, weird. Anyways, so I told you I talk about the gravitational constant varying. This is sea level anomalies right here. And as you can see, sea level is not the same depending on where you are at on the Earth. It varies. Some of it's due to tidal forces, and some of it's due to the gravitational constant differing over the course of the Earth, depending on, say, how thick the mantle is underneath it. If you've got like a lot more solid rock underneath you, more heavier rock, your gravitational constant is going to be higher. So it's a little bit of a mixture of both, but it still kind of corresponds. Like right here, it's got a much higher than normal sea level, which corresponds to over here on the second graph, which is gravitational anomalies, actually looking at the gravitational differences over the planet. Like there's a really low gravity here in northern India, southern-ish China area, whereas there's high gravity off that coast of China. So yeah, it can actually vary a little bit. It's maybe not enough to really notice, let's say if you had your GPS, but it's still a decent amount. I mean, this is in centimeters, so it can vary a span of 20 centimeters, which is pretty decent. That's almost about a third of a foot, roughly. But anywho, I just thought I'd kind of show that because I think it's kind of interesting. So developing a method for measuring mass. A mass operational definition will need common units, or a unit conversion factor to relate someone else's measurement to our own. For example, you could say 10 paper clips equal 1 bolt. This is important because let's say the Star Trek prophecies are true. In that case, in April 5th, 2063 in Bozeman, Montana, we'll make first contact with the Vulcans. Well, they might weigh themselves in green blood, because I think they have green blood. And, you know, we could figure out how much we weigh in green blood if, you know, this block of green blood weighs as much as, I don't know, 2 kilograms or something like that. That way we can kind of go back and forth between two different sets of units and figure out common ground. A good example of that is if you go to the Spam Museum in Austin, Minnesota, you will discover you can not weigh yourself. Well, that'd be actually kind of cool too. You can measure your height in Spam cans. I am 27 Spam cans tall. My wife is 26 Spam cans. If you know how big a Spam can is, say in centimeters, you can figure out how many centimeters you are. So, yeah, that's kind of why, so you can convert the two. Now, you don't need to go around weighing yourself in Spam cans or measuring your height in Spam cans, but you can, and I did. In some nuclear applications, there's some kind of weirder units out there, like 1 shake is equal to 10 nanoseconds. And there's some cooler things like a microcentury? Microcentury? I don't know. Oh, what was like a yeah, I can't remember, so maybe I shouldn't go with that. I'll come back to that thought. I thought there was a cool unit conversion in my head, but I can't remember off the top of my head now. In any case, we're going to use grams in this class. The standard unit for mass is a kilogram, but we deal with mostly smaller objects, so we're going to deal with grams. Okay, some common homework issues that I can see. If you ever make pictures, they're fine. Just make sure you label them. I've never really had an issue with that, but I've always kept this in here because I just want to make sure that you're labeling your pictures. Density is a characteristic property. Always remember that, because density is going to be intrinsic. I shouldn't use that word in this case, but it's always going to be associated with said object. You know, like iron's always going to have the same density, more or less. If you double the mass, then the volume will most likely double, but it's not 100% true, because if you double the mass, it doesn't always change the volume, depending on the situation, but it's likely that you're going to double the volume as well, but it's only if your density remains constant. So remember that. And make sure to put units in all your answers and always title your graphs. So those are things to know. And since I don't have the video, that's it for this video. A video inside of a video. Have fun. And I will see you in class on Wednesday.